typical students like at around 60 or so.
Hi everyone, thanks for having me here. I'm going to start my talk in a slightly unusual way with a little story. The last time I was here, 7 years ago, I came to give a talk when I was a student. And my flight here was 4 hours late, so I arrived around 1 in the morning, then I took my talk. I was detained at the airport because they didn't find my invitation letter satisfactory. They wanted my host's home phone number to confirm that they had really invited me here, because apparently I'm a shady character. And then Massey College forgot to put out the key for me. So at 2 a.m. I was on the street with no place to sleep, and I had to find a hotel. And then I woke up in the morning, the morning of my talk, losing my voice, and proceeded to give a terrible talk, in part because I could barely speak audibly, in part because I was a student who wasn't very used to giving talks. So 7 years later, I'm very pleased to say that Toronto's been a lot nicer to me this time around, and I hope in exchange to give a much better talk. It's so far, right? But you know, it's the time till the talk that counts, right? So I hope this time to give a much better talk. So I'm going to talk to you a little bit about where I see the field of weak lensing science going in the next decade. So I'm going to begin just with a little bit of cosmology background. So we have a whole host of cosmological observations that have given us a picture of the universe that has been confirmed in multiple ways. We believe that on large scales the universe is homogeneous and isotropic, spatially flat and expanding at a rate that is accelerating. And we have a theory of gravity, general relativity. So while this sounds like very nice, we have a whole list of things that we know, but as many of you know, our cosmological model also has a lot of incomplete details. To give you an example, we have our pie chart for the lambda CDM model, and we know the relative fractions of these different components pretty well, but at the same time, we don't actually know what these things are. So it's a little bit sad because we have this nice standard model of particle physics that does a really good job for this, but we don't really have theories for exactly what the dark energy and dark matter, which are these dominant components, are. We also have a nice picture of the sort of the timeline of the universe, that we have lots of structure now, and it came about because there were tiny inhomogeneities in the matter density. And then once matter was dominant, those inhomogeneities were able to grow to gravitational instability and create the kinds of structures we see here today. There are two types of cosmological observations that have been used to confirm this picture. So first of all, there are geometric probes. We have ways of measuring the geometry of the universe. For example, using standard candles like supernovae or standard rulers like baryon acoustic oscillations. And then we also have measurements of the growth of structure with cosmic time, back from the CMB when the perturbations were linear, to today when we have this cosmic web structure, which is in fact highly nonlinear. So the way I kind of see this picture is that we have a big picture which is observationally supported by multiple different observations, but at the same time, we're really not done because we have all these things that we don't really know about, like what are dark matter, dark energy, the nature of this early inflationary era, even confirming the theory of gravity as general relativity on cosmological scales. So there are a lot of things left to do, and what it comes down to for many of them is that the universe is dominated by these components which are dark, and we can't just go and look at them with our telescope. So we need some other way to observe them. So I'm going to talk to you in part about weak lensing and how we can use it to uncover some of these dark components of the universe. So the lensing deflection of light was originally predicted in Newtonian gravity, although it took general relativity to get the sine gate effect correct. And the standard picture that most people think of when they hear about gravitational lensing is something like this beautiful picture, which is strong lensing by a galaxy cluster. And so you have these dramatic arcs which are smeared tangentially around the brightest cluster galaxy and also around another bright galaxy. You know, it's not showing up really well on the screen, but there are arcs. They go like this. You might have to take my word for it. Thanks. That is better. So lensing, which is useful, is that the lensing effect is by all the matter along the line of sight, including the dark matter. So it's easy to look at this picture and say this cluster galaxy is causing this lensing, but actually it's all the dark matter in the cluster, and all of the baryonic matter that's causing that lensing effect. And if you were to guesstimate how big this lensing arc should be based on typical brightest cluster galaxy stellar masses, it would be a lot smaller. So I'm going to talk about weak lensing, which is a statistical effect. It's not as visually dramatic as that picture I just showed you. So to illustrate it, here we have an idealized background of perfectly circular source galaxies. And so then the question is, what does this look like if we were to plop a bunch of lenses in front of it? So the answer is that you get coherent distortions. So to give you an example, in this picture, there's a lens right there. And so everything is tangentially distorted around it. And there's a lens right here, so everything's tangentially distorted around it. So it's a similar picture of this tangential distortion, but the distortions themselves are a lot further because we measure it, all the way far away on cosmological scales, where the distortions might be order 10 to the minus 3. So there are two types of weak lensing measurements that people use. One is called cosmic shear. This is the one that's sort of gotten the most attention for cosmology measurements. So that's the autocorrelation of galaxy shapes. So basically what you do is you say, here's some distant source galaxies, and then the light from them has gone through this cosmic web that's been deflected maybe multiple times on its way to us, and so the shape has been distorted by those lensing deflections along the way. So the thing that we rely on is the fact that if you have two galaxies which are kind of nearby in the sky, they've been lensed by associated structures along the way, due to this cosmic web. And so their lensing distortions should be correlated with each other. And so that means their shapes are correlated, so you should get a non-zero correlation function of the galaxy shapes. In contrast, if you have two objects on completely opposite parts of the sky, they didn't pass through associated structure, and so their shapes should just be effectively random with respect to each other. So using this shape autocorrelation, we can build up a statistical map of the large-scale structure. So the other type of lensing measurement that's commonly used is called galaxy-galaxy lensing, or sometimes you'll see cluster galaxy lensing. So that's where we select a specific population of objects that we think are lenses. I've given an example here, just some bright-red galaxy. And we cross-correlate the lens galaxy positions with the shapes of the background source galaxies, these ones that are shown in black. You can see they have some tangential distortion. I'm not very good at drawing on the computer. I tried to show that it gets weaker as you're further away. But basically what this tells us is about the total matter distribution around our lens galaxies or lens clusters. So that's like the galaxy mass cross-correlation function. Again, this is all the matter, including the dark matter. So to give you some sense for the state of the field and how things have gone, the first detections of weak lensing by galaxy clusters happened quite a while ago. It was in the mid-90s. And then in 2000 and 2001, there were the first detections of cosmological weak lensing, this cosmic shear measurement. So those were sort of, 4 sigma, 5 sigma detections. They were enough to see that the effect was there, not to get precision constraints on cosmological parameters. So then in the past decade, it's been this sort of game of getting larger data sets and making increasingly precise lensing measurements, getting the errors down to sort of 5 or 10% level, which is starting to become interesting cosmologically. Next year, several large ground-based surveys are going to start measuring lensing to 2% precision, which is going to get very interesting. And then at the end of this decade, at least 2 large missions are going to start measuring lensing with sub-percent precision. So we've made a lot of progress in the past decade, and we're about to be inundated with data. To give you an example of one of those surveys that's starting next year, I'm going to talk about the one that I'm involved in, at the Subaru telescope. So the Subaru telescope has an 8-meter primary mirror, and it's located on Mauna Kea, which has excellent imaging conditions. There's a diagram here where you can see the different positions where there are instruments. So I'm talking about a prime focus instrument, which goes all the way up here. So the Subaru telescope is already well known for having many instruments that can be used for optical and spectroscopic observations. For example, for optical imaging, there's SupremeCam. So this is an example of an image from that particular instrument, looking at a redshift 0.8 galaxy cluster that was discovered by the ACT collaboration through its SD effect. So we recently used the Subaru telescope, particularly a student, Bruno Miyataki, led an effort to use the Subaru telescope to estimate the mass of this cluster via weak lensing. So you can kind of see here, you can see the red cluster galaxy here, and you can see there's a concentration of some reddish galaxies in the cluster. And then we measure the background galaxy shapes to get a cluster mass. So the survey that's going to take place starting next year will use a new instrument called SupremeCam, HSC, not to be confused with HST. So SupremeCam, the existing instrument, its field of view is shown here, and then this is the field of view of HSC. It's 1.5 degree diameter. So the basic idea is that if you increase your field of view by a large amount, then it doesn't take nearly as much time to make a very large survey that you can use for large-scale structure measurements. So HSC went on the telescope back in August. To give you a sense of scale, this is a picture of the HSC with its wide field corrector, and it's a lot bigger than a person. And then here it is. This is a picture taken from the perspective of somebody on the floor of the telescope facility, and then HSC is way up here near the top of the dome. This is from when they were beginning to take images. I think they actually started by having a video camera mounted on HSC and using a video camera to make sure it was placed properly. But you can see more about this on the HSC blog at NAOJ. A lot of things are happening now that it's actually on the telescope. Okay, so we planned a 3-layer survey using this instrument. So the survey layer which is most relevant for me is the wide survey layer. So that's a 1,400 square degree survey, which will be in 5 bands, going to an I-band depth of 25.8. And the scientific focuses will be weak lensing and also galaxy populations. And then there are 2 other survey layers which get progressively deeper and also covering smaller areas, of course. So there's a deep layer which will be used for a number of different applications, taking advantage both of the 5 wide band filters and also 3 narrow band filters. And finally, there's an ultra-deep survey, which is just 3 square degrees and goes even deeper. This survey also has some important synergies. We have CMB measurements from ACT, and we'll eventually have ACT pole as well. We have redshifts. The survey overlaps completely with the SDSS 3 survey, BOSS. And we have the deep fields overlap with surveys that have near infrared data, UBAM, and so on. So just as a reminder of what's driven this development, sort of a decade ago, people started to realize that cosmic shear is an incredibly powerful way to probe dark energy. So what I've shown here is the predicted cosmic shear signals for the LSST survey, and that's in a number of different redshift bins, going from lower redshift to higher redshift. And the fact that this lensing signal is getting higher is a reflection of the fact that we're probing further away. There have been more lensing deflections, and we can use this to probe the growth of structure in the universe, which depends on the equation of state of dark energy. And so you can see that in terms of this, essentially this is just a Fisher matrix analysis showing how well we can do for dark energy constraints. And you can see, for example, that so the weak lensing is this blue curve, and it's shown here with a number of other observations like variant acoustic oscillations. And so you can combine them all together and get a really nice tight constraint. So again, just as a reminder, the cosmic shear is measuring the matter power spectrum. And another reason this is powerful is that if you compare it with, say, measuring the galaxy power spectrum using a redshift survey, the galaxy power spectrum has this galaxy bias factor, which is kind of a nuisance, whereas the lensing is measuring the matter power spectrum, which can be much more easily predicted theoretically. But there's almost always a but in any measurement when anybody says this is really easy and it's going to be incredibly powerful. You have to ask, is that all there is to it? So the answer for weak lensing, as for pretty much any observation we use now, is, that's not all there is to it. There are some complications. So the picture I've shown here illustrates one issue, which is the issue of measuring the lensing shears, the lensing deflections. So we have some intrinsic galaxy with some unknown shape, unknown morphology. Then it gets sheared. So the picture shown here it's exaggerated. This is a larger than cosmological shear. You can see it's stretched out horizontally. So all we want to know about is that one step from this first picture on the left to the next one. But the problem is there's a lot of other garbage that happens to our images. So the light has to pass through the atmosphere if we have a ground-based telescope, through the telescope optics, regardless of whether we're on the ground or in space. So that causes a convolution, some blurring, and so you get this thing here that's significantly blurred out. And then detectors measure a pixelated image. You can think of that as a convolution with a top hat filter and then sampling at pixel centers. And finally, the image contains noise. And in fact, our weak lensing measurements are typically dominated by galaxies with signal to noise of 10 to 20. So the noise issue is even worse typically than what's shown there. So cosmic shear, like I mentioned to you, is an autocorrelation of shapes. So we take the shapes of pairs of galaxies. And what this means is that if we have some multiplicative bias in the galaxy shapes, that's obviously going to be a problem. We can have another problem, which is coherent additive biases. So the way those can come about is that this blurry kernel, this convolution kernel, the point spread function, is not typically circular. It's typically anisotropic and coherent. So in other words, it has some anisotropy which is coherent across large scales. And if that's not removed perfectly from the galaxy shapes, then it's a coherent shape distortion. It looks like a lensing signal, and it adds to our cosmic shear. There are other problems as well. Everything I've been telling you about assumes the galaxy shapes are random in the absence of lensing, and in fact we know that's not true. There are intrinsic galaxy shape alignments having to do with alignment with large-scale tidal fields. So that causes our basic assumptions to be violated, and that's another source of coherent galaxy shape distortions. There's some theoretical uncertainties that have to do with, for example, predicting the matter-power spectrum on small scale where baryonic effects might be important. And then there are uncertainties in the photometric redshifts, which we typically use to estimate the distances to our source galaxies. So what do we take away from all of this? Well, I told you our data sets are going to get bigger. And that means our statistical errors are getting smaller. And that means our systematic errors also have to get smaller. Okay, we don't want our measurements to be dominated by systematics. So in the past few years, we've seen a kind of change of perspective. Initially, we were focused pretty much exclusively on cosmic shear for cosmology measurements. We still think we should measure cosmic shear, but people have also started to realize we should identify combinations of lensing measurements and other measurements that will allow us to directly calibrate out some of these systematic errors. And we don't want to have to assume a model for them. We want to be able to marginalize over them somehow by using as much information as we can possibly get, and then minimize the combination of the statistical and systematic errors. So just to summarize what kind of data we'll have, so we'll have a lensing shear field. For example, in the next few years, we'll have one from HSC. So you can get the lensing shears in some grid. It might end up looking something like this. We also have the 2D galaxy density field. By 2D, I mean this is imaging data. We might have photometric redshifts, but they're not great, so we can think of it as a 2D field. Now, in some cases, we'll actually have the full 3D galaxy density field and velocity field by having a spectroscopic redshift survey. For example, from BOSS. So HSC will overlap entirely with BOSS, but not all of the imaging surveys that are starting soon will overlap with the redshift survey. So some will have this information, some will not. We can also get other observations not in the optical. For example, X-rays. We can have X-ray measurements of clusters. For example, again, at HSC, we'll have some area that overlaps with XMM. And there are measurements of the CMB, for example, that gives us SE measurements. So this, for example, shows over here, the color shows the contours of the SE, and these black circle contours show the X-ray emission for one particular cluster. So we'll have those additional observations that help us map out the cluster field. We can also use ACT-GOAL to measure CMB lensing. And finally, lensing doesn't only lead to a shape distortion. It also leads to a magnification, which changes the number density of objects and the brightness. And there are many efforts underway to try to coherently measure both the lensing shear and magnification, and therefore get more information. Okay, so this is actually a lot of data, and many people have been thinking hard about how can we use it to sort of make optimal cosmological measurements. So if I had to say what our approach would be in sort of one sentence, it would be cross-correlate everything with everything. It's a bit of an oversimplification, but the basic idea is if you have systematics in one measurement, you don't want to focus only on measuring that one thing and autocorrelating with itself. You want to cross-correlate it with something that has completely unassociated systematic errors.
I mean, why is it that the cosmic shear is the thing rather than the differential? I mean, why do you tend to focus on it first?
So I think, well, the basic idea, I think, was just that it's easy to define like what's a null test, like in the absence of lensing and intrinsic alignments, but ignore those two. Then galaxy shapes should be random, and if you start, especially the additional lensing measurements were cluster galaxy lensing, so you could just look at background galaxy sources with respect to the cluster position and say, well, they should just average out to 0, if there's no lensing shear. Whereas for magnification, there's some, sort of default number density of sources, and you have to measure that very carefully and make sure you're not affected by other things that happen in clusters, like there's ICL and there's a higher number density of galaxies. It's harder to measure the sky level properly, and that can, even issues with photometric calibration, those can all mess up a lensing magnification measurement. And so,
I guess my thought on this was that we can measure. I would have thought photometric measurements are more accurate, more precise. Maybe that's not the case.
So, I mean, the photometric precision, if you look at like the photometric calibrations of surveys, things have been improving. So we have, the SDSS has this Uber calibration procedure, which gives a stable photometric calibration at sort of 1% level. But it turns out, like, if you look at what level of photometric calibration do I have to do? Do I have to achieve to get a really robust cosmological magnification measurement? It's even better than that. Okay, so this is what I was saying before. Basically, you cross-correlate multiple different probes together, you have more information, and you can make a measurement which is less sensitive to one specific method's observational uncertainties. So, going back to this idea of cross-correlations, I've mentioned to you one particular type of cross-correlation, the galaxy-galaxy lensing. So unlike cosmic shear, that's just one shear field cross-correlated with a specific set of lens positions. So people typically say, well, we can't really use this for cosmology. It's measuring a galaxy mass correlation, not the matter correlation function. But if we combine it with the galaxy autocorrelations, it turns out that we can typically infer a matter power spectrum. And like I mentioned before, it's observationally easier, because of the fact that it's a cross-correlation. So some of the issues for cosmic shear simply don't turn up in this measurement at all. So just to give sort of schematically like how that works exactly. So if we have some lens galaxy sample and we have spectroscopy, we can measure its 3D correlation function. You measure some projection of the galaxy mass correlation function using the galaxy-galaxy lensing. So schematically, you can put those two measurements together, lensing squared over the clustering. And what comes out is the nonlinear matter power spectrum, or correlation function, sorry, racist in terms of correlation functions, with the matter density in front of it. And this thing, this RCC. So what that is the cross-correlation coefficient between the galaxies and the matter. So that seems like a nuisance, and I will get back to that in just a moment. So there's another place where cross-correlations can help us. So that is when it comes to baryonic effects on the matter-power spectrum. So people pointed out that this is a possible interpretation problem for cosmic shear. So the plot that I showed here came from a paper about 4 years ago. What it shows is the concentration parameter of the dark matter halos as a function of the halo mass. So there's the total concentration and the dark matter only concentration. And so basically the black points down here comes from dark matter only simulations. And then the blue comes from hydro simulations. So there they have actual baryonic Kool-Aid to form stars. And you see that the concentrations go up by, something like 40%. Now, it turns out that those simulations form too many stars. There's an overcooling problem. So this is an exaggeration. We don't expect, sorry, Dropbox. Feels like it wants to tell me something. So we don't actually expect reality to be quite this bad, but maybe it's somewhere in between. And we might have to worry about this. Because as the matter becomes more concentrated, that changes the matter-power spectrum. Not just on scales inside of halos, but that concentration happened in part because it changes the amount of matter outside of those halos as well. And so that can extend to a few times the virial radius. So in a follow-up paper, the same group actually showed that if you include galaxy-galaxy lensing with the cosmic shear, you can actually calibrate this effect out, because the galaxy-galaxy lensing lets you measure the matter distribution around galaxies, as in their dark matter halos and surrounding their dark matter halos. And so you could effectively measure this concentration mass relation and then feed that back into the cosmic shear measurement. And part of this is possible because if you have lens redshifts, then it lets you localize what's going on at particular physical scales. So for cosmic shear, it's measured typically as a function of angular separation. So it mixes up physical scales depending on what redshifts the galaxy pairs are at. Whereas if you have a specific set of lenses and you know the redshifts, you can essentially isolate what's happening as a function of scale within the dark matter halo and outside of it. Okay, so then we could say, let's use all three things. Let's use the cosmic shear to get the matter clustering, and also use the galaxy-galaxy lensing and the galaxy clustering. So it turns out that these measurements depend in very different ways on systematics like intrinsic alignments and shear measurements. So essentially, a few papers have shown that if you take cosmic shear alone and you try to model out these systematics, you lose your cosmological constraining power because you have too many nuisance parameters to marginalize over. But by adding these measurements in, which are sensitive to those systematics in a different way, you can essentially regain all of that cosmological constraining power, despite the fact that you have these expensive systematics models. So your statistical error essentially remains fixed, and your systematic error gets smaller when you do this procedure. So I want to give you a specific example from analysis that I was part of using the SDSS data. I was part of with a large group of other people who are named here. So going back to this slide where I talked about combining the galaxy-galaxy lensing with the galaxy clustering to get the matter-power spectrum, and I pointed out to you this cross-correlation coefficient, which seems to be kind of a nuisance in this measurement. You don't really want it to be there. It would be nice if it were 1, and in fact on large scales we have every reason to believe that it is 1, but not on small scales. So the problem really is the small scales. So there are these uncertainties in the matter surface density. The sigma is the projected surface density, which is what we're sensitive to for lensing. So there are a few uncertainties. There are these baryonic effects. There's this cross-correlation coefficient, which is not 1 on small scales. So you might say just don't measure the small-scale lensing signal, don't use it, and you'll be okay. But it turns out that that doesn't really work. The reason for that is with lensing, you don't actually directly measure sigma, or surface density. You measure delta sigma, which is the average surface density within some radius minus the value of that radius. And of course, if you measure the average surface density within some radius, so the problem is this integral goes down to a radius of 0, where there's all kinds of stuff that we don't really know about and maybe we don't want to have to worry about. So one solution that we proposed is to define a statistic that we call the annular differential surface density. We denote it epsilon. So we simply take our measured lensing signal and we subtract out the lensing signal at some radius that we call R0, multiplied by this ratio here. So this quantity goes to 0 at R0, and on large scales it looks like the lensing signal. So if you write down what does that do, what is epsilon in terms of the surface density, you get this long equation. Basically, you can convince yourself it doesn't depend on anything that happens below R0. So if you have some scale below which you say, you know what, I'm not really sure what's going on down here, you know, this cross-correlation between matter and galaxies is maybe too far from 1, or maybe I think barometric effects are bad, I'm going to choose that R0 and get rid of everything below those scales. So to give an example of how that works, what I've plotted here is the cross-correlation coefficient, that RCC, the cross-correlation between matter and galaxies, as a function of radius. So these points up here are what that cross-correlation does if you use the lensing signal itself, that delta sigma statistic. So you can see that here's 1, this horizontal line, which should be there. It's not drawn there. Sorry. So these points become very different from 1. It's about 10% off from 1 at 10 megaparsec, and then it just shoots up. It's really a mess. And so if you had to model this, it would depend in very great detail on how galaxies populate halos. It's kind of a messy thing you might not want to be modeling at all. So if we use this epsilon statistic, and we say get rid of everything below 3 megaparsec, these points with error bars show what the cross-correlation does. This cross-correlation coefficient is at worst 0.96 at R0 itself. There's also, you can see line that goes through it. That's not a fit. That's actually a perturbation theory prediction. So you're able to predict that because you've gotten rid of what happens inside of dark matter halos. In contrast, you can't make such a prediction for this curve up here because it depends on all kinds of messy things that would require you to go to extremely high order to model. So then, if you...
Sorry, what's the other line?
So this line and this line, it has to do with which order of perturbation theory you go to. So if you then try to use this epsilon statistic and reconstruct the matter epsilon, the epsilon matter here, then basically the points with error bars are the actual one in this simulation, and then the red line, I mean, the points are what you're reconstructing, and the line is the actual epsilon matter. You can see we reconstruct it extremely well. The other thing to notice on here is this dashed line. So that would be the linear prediction. So this is just to emphasize to you, we're still measuring the nonlinear matter power spectrum. We have to compare with those predictions, not the linear one. So I just told you we're getting rid of a bunch of information below a few megaparsec. So you might ask, did I get rid of some of my ability to constrain cosmology? So this plot shows that that's essentially not the case. So basically the black line is this epsilon matter for some fiducial cosmology parameters over here. And then all these other colored points and lines are the prediction for different cosmological models. And so you can see that, if you vary sigma 8 by 10%, then this changes by a significant factor by about the amount you would expect just for the lensing signal itself. So this is a really nice statistic. And so I'm going to show you some results where we actually use this to make cosmological parameter constraints. So for lenses, we use spectroscopic samples from the Sloan Digital Sky Survey. There are a few different samples that we use. We use luminous red galaxies at redshift 0.3, and main sample galaxies, which is a flux-limited sample of galaxies at redshift 0.1. And then we have about 60 million thinner galaxies that we use as sources. Another important aspect of this analysis is that we do the analysis separately for the different galaxy samples. We don't just lump everything together. So the merit of doing that is that if you measure the clustering, say for luminous red galaxies, These are massive galaxy samples, and so the clustering should be very high. They're highly biased objects. But if you then take the lensing and reconstruct the matter-power spectrum, it has to be the same, no matter what galaxy sample you use. And if you don't get the same thing for your different galaxy samples, it means that there's some problem with the assumptions. You maybe chose a bad choice or not. Maybe you just have some weird lensing systematic. So there's an advantage to doing this for a few different galaxy samples and then combining afterwards rather than combining everything at the very beginning. So to give you a sense for what the current data look like, this is the measured lensing signal for luminous red galaxies as a function of transverse separation. So the transverse separation runs from 50 kiloparsec to 60 megaparsec over here. And you can see that the signal is very well measured on all of those scales. So this blue line roughly marks the transition from the one halo term, where we're measuring the lensing due to the halos that these luminous red galaxies live in, to the cosmological lensing term, where we're measuring lensing by large-scale structure. So here's a plot of all of the lensing data that we used. So the red line is the same as the data on the previous slide, it's just that it's bid more finely. And then there are two other galaxy samples shown on here. So for perspective, if you look at the horizontal axis, you can see that we're measuring shears down to the few times 10 to the minus 5 level at few degree scales. So the bottom curve shows this upsilon statistic that I've been talking about that gets rid of everything below, in this case, 2 megaparsec. This is actually R times upsilon. So you can see immediately that this quantity is a lot noisier. That's because we have just a lot of signal to noise over here that we're getting rid of, basically. So the shape noise, the noise due to the random galaxy shapes, is more important in this upsilon statistic. This is a plot of the clustering data, the projected correlation function up here for the same set of galaxy samples. And then the clustering upsilon statistic. Here we use R naught of 4 megaparsec. You can see immediately if you flash back and forth, this is the lensing again, here's the clustering. You can see that the clustering is higher signal to noise. So the lensing is our sort of limit for how well we're going to be able to do with this data set. So our actual procedure doesn't involve taking ratios of noisy quantities. Instead, we directly fit those quantities. So to directly fit those quantities, we need a model for the nonlinear matter-power spectrum, which is accurate down to a few megaparsec. And we also need the full nonlinear galaxy bias. So we have a perturbation theory motivated expression for the nonlinear galaxy bias, which has two free parameters, which we're then going to marginalize over whenever we want to make a cosmological parameter constraint. So for example, if we take these data, the data I showed you on the previous slides, and we fit them for sigma 8, the amplitude of matter fluctuations, omega matter, matter density, and we fit them for the galaxy bias, those three parameters, and we marginalize over the galaxy bias and the lensing calibration, then we get this constraint shown here in terms of sigma 8 and omega matter to a power. And you can see we get 0.8 plus or minus 0.05. So this is a pretty nice tight constraint with an effective redshift of 0.25. So just to give you a sense of perspective of how this combines with, say, CMB constraints. So that's shown in this plot. So basically, this is a sigma 8 versus omega matter plane. So these bananas that go in this direction, those are the 1, 2, and 3 sigma constraints for our data. So that corresponds to this constraint here. The red open contours are WMAP7. And then these colored contours are what happens when you combine the WMAP7 data with our data. And so you can see that the contours, the size of the 1 sigma contour is roughly half when you add our data. And it's really nice that the degeneracy directions are so different, because that's what really helps us here. Then you can extend to more general cosmological models. For example, you can allow the model to be non-flat. You can let the equation of state of direct energy be a constant but not fixed to -1 as it was on the previous plot. And so then what these contours show, the open contours are the CMB WMAP7 data. And the colored contours are when you add our data to the CME. So for example, in this bottom plot, this is a plot of the curvature versus the dark energy density. And you can see that by adding our data, we essentially get a solution which is around the concordance cosmological model. It's roughly flat universe with dark energy density somewhere a bit above 0.7. So to compare this with cosmic shear results, so there have been a few different cosmic shear results recently which have statistical power around 11%, 6%. These are typically at higher redshift. So the effective redshifts are something like 1 and 0.8, whereas our effective redshift is 0.25. It just so happens that SDSS has better control of redshift systematics. This is just because SDSS is shallower. Usually being shallower is bad, but it does mean that if we want a complete spectroscopic sample to our full depth, we have it, and those surveys don't. So, if you compare that versus our constraint, which is, similar to this 6% constraint, then the results shown here establish SDSS among some of the most competitive surveys for weak lensing cosmology. Now, the ideal thing to do really would be to take, say, CFHT data. The CFHTLS lensing results are now coming out. Those will be even more powerful than this one that's shown up here from 5 years ago. The really interesting thing to do will be to combine those with ours, because the effective redshifts are so different that you'll be able to say something about the evolution of structure with time. And I just want to point out, the thing I mentioned that we're limited in the signal to noise due to just the lensing noise. So what I wanted to show you is that if you have the Gauss galaxies and you measure their lensing using HSC, they're somewhat less dominated by the statistical error. So the black points with errors are the allergy measurements I just showed you. The red is our prediction for HSC. And the bottom shows the inverse signal to noise. So you see that Gauss allergies with HSC as sources is generally doing better than our current measurements, which is really nice. Okay, how am I doing for time? Sorry.
Well, 7 minutes.
7 minutes? Okay. So I just want to quickly show you one more application. So I just focused, going back to this plotted LRG signals, I just focused on what can you do with this cosmological signal on large scales. But the small scale lensing profiles are really useful, right? Everything to the left of this line. It tells you something about the dark matter halos that galaxies live in. So it lets you learn something about the galaxy-dark matter connection, which is intrinsically interesting if you want to learn about galaxies and their formation and evolution. But it can also, it turns out, help us with cosmology. So an example of how we can use this, I'm going to talk briefly about the fingers of God effect. So this plot shows a contour plot of the 3D galaxy correlation function, okay, where the horizontal axis is transverse separation and this vertical axis is the line of sight separation. So the thing about galaxy surveys is that, of course, they give us a 3D density field, but in fact, when we measure the redshift, it's the sum of the cosmological redshift plus the peculiar velocity. And so that third dimension along the line of sight is not really the same as the other two. So you get an effect that looks like this one. So on large scales, this indicated by these arrows, there's some squishing of the contours with respect to a perfect circle. And the reason for that is just, structure growth. You have big, large-scale sort of infall, and that's going to turn out to squish the contours. Things are falling towards each other. But there's also this effect on small scales, which is often called the fingers of God effect. It's a small-scale effect due to the velocity dispersion within dark matter halos. If you have, say, a few galaxies inside of a halo, then they're orbiting with respect to the halo center, and that tends to smear everything out in this line of sight direction. Okay, so for the SDSS galaxy power spectrum analysis, some people said, hey, maybe we can solve this effect by simply identifying dark matter halos. So we try to say, here are these 3 galaxies, they're really close together, they're in one dark matter halo, so I'll only use one of them to represent the halo, and then I'll get rid of this fingers of God effect. So it turns out that doesn't work perfectly. If you're trying to measure these redshift space distortions, you can't fully get rid of the fingers of God effect just by choosing halos, unless your chosen halos are really at halo centers. Imagine if you choose one galaxy in a halo and it's not at a center, it's still orbiting with respect to the halo center. And that's going to cause some systematic effect in the redshift space power spectrum. So there was a paper last year by these guys, led by Chiaki and Kage, for how to calibrate out this fingers of God effect. So the idea is to, again, take advantage of the synergy between spectroscopic and photometric surveys. So you use the spectroscopic survey to select halos. And then you focus on the halos that have multiple objects in them. And you compare a few different measurements. So you say, for this halo, I'm going to choose the center in different ways. Maybe I'll pretend the brightest galaxies are the center. Then I'll pretend the faintest galaxies are the center. Maybe I'll take the mean position as the center. Play around, choose different centers, and then make different measurements. Measure the redshift space power spectrum, the galaxy-galaxy lensing, which tells you about the matter distribution and offsets within the halos, and even the cross-correlation between your galaxies and the photometric galaxy distribution. So it turns out that those measurements are sensitive to these offsets within halos in different ways, and you can try to model them. So we had a paper last week where we tried to put this idea into practice. So in order to do this, you need some halo model for how do galaxies populate halos as a function of the halo mass. Then you have to include a number of parameters, like if you have, say, your brightest LRG that you use as a proxy for the center, you have to assume some fraction of them are actually at the centers and some fraction are offset. For those that are offset, you need to assume what is the spatial offset distribution and the velocity distribution. And then you're going to start modeling all of those offset-related parameters. So I've shown an example here of how we did this for the cross-correlation between our halos and photometric galaxies, where on this panel we use the brightest LRG as the center. Here we use the faintest one, and here we use the mean position. So you can see the black points with errors of measurements, and you can kind of see that the shapes of these curves are different for the different choices of centers. And we know that we're using the exact same sample of halos. The intrinsic halo properties have to be the same. What's different is where we're located within them. So we can model all those offset distributions, and you can see that the model we've adopted does a very nice job. That's the red line gives all the components of our model, and it matches the data very nicely. So if you ask then, what are the model parameters for those nice models I showed you? We found, for example, that if you have bright, luminous red galaxies in these halos that have multiple LRGs, and you just assume the brightest galaxy is at the halo center, then 40% of the time you're wrong. 40% of those bright LRGs are actually offset within the halos. If you use the faintest LRG, 70% of the time they're actually satellites. So that trend goes in the direction you would expect. Faint galaxies shouldn't be at the center if there's a brighter one. But it's not like this is 0% and 100%, which you might have naively expected. For those that are offset, the typical off-centering radius is about 400 kiloparsec. So it's a Gaussian distribution with that as the characteristic offset radius. And the typical velocity dispersion in these halos is 500 kilometers per second. So then you can ask the question, let's say we don't model this effect. Let's say we ignore this and think we have measured halos perfectly. What would be the effect on measuring cosmological parameters using the galaxy power spectrum? So in this plot, we show the change in the halo, the relative change in the halo power spectrum. So the red line is how much it gets changed by having neutrinos with a sum of neutrino masses of 0.1 eV. So that's an example of something you might try to measure using a large-scale structure measurement. So the other lines have to do with our measurements, our constraints. So we make a few different sets of assumptions. The blue line, the one that shows very little change in the halo power spectrum, is what happens if we assume that these multiple LRG systems that we use for this measurement have this fingers of God effect, but all the single LRG systems don't. So it's an incredibly optimistic assumption. You're saying all single LRGs are at the centers of the halos that they live in. Okay, so that's definitely way optimistic, but it's worth plotting that line on there. And it turns out that at K of 0.3, of the fog effect as the bright galaxies in multiple LRG systems. So we scaled things appropriately, like the offset radius gets scaled with the Barrow radius. For lower mass halos, it's a smaller offset. But we assume similar levels of offsets, like 40% of single LRGs or satellites. And this is, pretty likely a worst case. So that's at the bottom of the allowed curve. You can see that, this red line, which again would be an interesting thing to measure, falls somewhere in the middle. So if reality is closer to our worst case scenario, then we would have a real problem trying to measure neutrino masses using the galaxy power spectrum. The final curve that's on here, this purple curve, is what happens if we try to measure the lensing and clustering signals for single LRGs and try to model it using the model from this paper. So that's a somewhat dubious thing to do. The reason being that in the multiple LRG systems, we could directly constrain the halo concentration by combining all the different measurements of the different centers. Whereas for the single LRG system, we only have one LRG, we only have one proxy for the center. So we have to make a number of additional assumptions about dark matter halos. So still, it is kind of interesting. It falls sort of smack in the middle of this allowed envelope. Okay, so our conclusion based on this is that this fog effect is something that will need to be calibrated out if people want to use the full galaxy power spectrum to do cosmology with surveys like FLOS. So to conclude, galaxy-galaxy lensing measurements can be used to test our theoretical predictions for how galaxies and dark matter relate to each other. It can also be used to constrain cosmological parameters at various redshifts. And the reason for this is that lensing is the only technique that directly probes the total matter distribution, which is what we really need to know about. And in the future, in the next sort of decade, we're going to have better signal-to-noise. And so we'll be able to make cosmologically interesting constraints on structure growth. And most likely that's going to happen using interesting combinations of multiple observables to get an optimal error that is lowest combination of statistical and systematic error.
How small scale can you go? Can you start using this to code for alternatives to the CDM and get at like warm dark matter or self-interacting dark matter? You can start smoothing out internal structures of halos.
So what scales would you have to get down to?
To see, it would be really interesting if you could see like the cutoff in the matter power spectrum at the order of 5 to 10 inverse megaparsecs, or cutoffs from smaller than that.
So that's getting a little bit tricky, I think, because of some of these other effects, into alignment and other things. When I think of using deep lensing to probe gravity, I think of more like the large scale constraints where you can use it essentially to, especially if you combine it with, say, redshift space distortions, then you can probe growth and structure and also the ratio of metric potentials using it. And I think that's going to be the way forward for using lensing for extreme gravity.
That's a related question. Thinking about the run density inside your halos.
Say anything on
The run of density inside your halos.
oh the radial density profile.
Yeah.
Yeah. So people certainly have done this. For example, they tried to constrain the concentration mass relation for galaxy clusters, and also to a degree for galaxy mass halos, where the complication there is that for galaxy mass halos you have to stack a lot of them, so that interpretation in terms of the density profile gets more complicated. People have done that, so it would be a little harder to say, what's the inner slope of the density profile. That gets more complicated, but concentrations are certainly quite doable.
What about bispectrum?
Using the lensing bispectrum to
Well, maybe non-Gaussian spectrum. What can you say about the non-Gaussian analytic non-linear? We evolve knowledge.
So, I haven't looked into this as much. I certainly know people have talked about using lensing bispectrum to get at the matter bispectrum. thing about that I think is a little more challenging is it turns out if you take our current knowledge of intrinsic alignments of 2-point functions, and then you say what are the implications for the 3-point functions, the lensing 3-point functions will be significantly contaminated by intrinsic alignments. And so in practice, it would take some really careful modeling to use that measurement effectively. I think it's doable, but challenging.
So the error bars on correlation are correlated, right?
Yes.
Why don't you use nice cross spectrum instead, and then with a cutoff where you don't believe your small scale anymore, you use CM instead of 2-point correlation.
So, well, there are a few answers to that. First of all, we felt that there is an advantage to be gained for the lensing measurements, especially to having things in terms of a physical scale instead of a scale, which mixes up physical scales. And in terms of the correlations between radial bins, I mean, it's true, it's there. We saw that as something which is modelable. And so we just said, okay, you know, there's an advantage to working in terms of physical scale, and then we'll just model those complications out.
And so if you use this, if you use your measurement with CMB lensing power spectrum that measures the omega lambda very well, won't you get much better constraints on omega lambda versus square shares?
Yeah, I think, so that's one of the key measurements we have planned with HSC. We want to combine our lensing, our galaxy lensing measurements with the with act pole measurements of CMB lensing, and also the act pole versus HSC cross correlations, so CMB and shear cross correlations. And yes, that definitely will be a very useful thing.
So for the galaxy lens, as I understand what you're doing is you're identifying a galaxy as a lens, and then you're cross-correlating the shapes of all the surrounding galaxies by the distance to that lens galaxy that you've identified.
Yeah.
How sensitive are you to mass modeling within the lens galaxy? If it has a big massive subhalo off center somewhere, how does that affect your results, or how much information can you extract about the substructure within the lens?
Well, so there's a distinction to be made here, because for cluster galaxy lensing, people sometimes measure cluster galaxy lensing for a single cluster lens, and then you're fully sensitive to all kinds of funny business, substructure, triaxiality. For our measurements, we're taking many, many galaxies stacked together, and so we effectively can't really say anything about issues like substructure. And in principle, with if we select galaxies based on the photometry, we're getting an intrinsically spherical mass distribution when you average over enough of them as well. So we're not really sensitive to that. We're sensitive to the average profile.
But I guess the average profile. You mentioned you're sensitive to kind of average concentration.
Yes.
Comment on the observational program that you would see that you have in place to figure out which of the scenarios you have in the punchline plot. So if you had to model, if you had to determine those parameters better, how would you result?
So there are a few things that we're going to want to look at. When we have a combination of HSC and BOSS, I think that will help us somewhat, because if you think about what we'll actually have, so BOSS is a higher number density. So this sample is 10 to the minus 4 number density, 10 to the minus 4 inverse negative. And BOSS is a density 3 times higher. And so if you look at what that actually means, there are somewhat more halos where you have multiple objects in them with redshifts. And so you'll be able to do, like, to give you an example of what this came from, we took this LRG sample and defined halos, and only 5% of the halos we identified had more than one LRG. Like 95% of the halos had one thing in it. So when we took our multiple allergy sample and started doing stuff with it, we were just limited by size.